Good morning, students. In today's class, we will discuss about controller tuning methods. Controller tuning is another important article where the controller parameters, that is, mostly the controllers are PID controllers. For proportional controller, the controller parameter is proportional gain or proportional band, that is inverse of proportional gain. For integral action, the controller parameter is integral action time Ti, and for derivative action, that is derivative action time Td, or the inverse, that is the reset rate and derivative action constant, that is Td and Ki and Kd respectively. So how these parameters for selecting these PID controller parameters, the methods are within the controller tuning scope, and there are several methods for controller tuning. Mostly the methods are experimental methods. We should know what are the features based on which the controller parameters are to be chosen or controller tuning are to be performed, and what are the different experimental methods and models are available. So these are the topics which we should cover within the controller tuning methods. Since we have already covered controllers, pneumatic controllers, electronic controllers, so in next level, the operation of controller is important. So for controller operation, the most important topic is the tuning methods. That is how these tunings should be adjusted. And the process for experimentation for obtaining the optimal values of what is tuning? Tuning means the process of experimentation for obtaining the optimal values of the controller parameters with respect to a particular process is known as controller tuning. First thing is, this is a typical process dependent. This is for particular process, not that a controller is tuned means it will work for all the process control systems. This is for a particular process control system. So, and this is the process of experimentation, that is the process of choosing the optimal values of the controller parameters. What I have already mentioned, that controller parameters means for proportional, that is the proportional gain or proportional band. For integral and derivative control systems, integral action time or derivative action time are the parameters. So choosing the optimal values of the controller parameters for a particular process is known as controller tuning, and this is very much process dependent, and any improper selection of the controller settings may lead to instability or deterioration of the performance of the typical system. So this is the closed loop control system for generalized any process control system, where this is the process and the output, this is the feedback process, and the controller is operated by depending on the error signal generated from the due to deviation of measured signal coming from the process output through measuring system comparing with the set value. So the response or the controller output is, as we all know, that this is for proportional control system, that is Kp into Et. This is the error signal Et. Then this part is for derivative control action, Kp into Td, dE dt. plus Kp by Ti integral 0 to T et dt. That is for integral control action, where this Kp, Td or tau d, whatever derivative action time, and Ti, the integral action time. So these three are the parameters, and objective of controller tuning is to find out the optimum values for these three parameters. Now the basic criteria which is required to be satisfied in order to obtain the best performance, that is these are the most important features based on which the controller tuning is performed. So what are the parameters? So the parameters are decay ratio and the different error signals. The decay ratio and the error signals. What is decay ratio? Decay ratio is the ratio of second peak overshoot to first peak overshoot, and that should be within 1/4. The value of the decay ratio should be 1/4. Normally the response characteristics is like say if the set value is if this is the maximum response point, then the value is like it goes some overshoot and undershoot, and after certain oscillation it reaches to the steady state value. This is the normal procedure of attaining the steady state condition of a process value. So this is the first peak overshoot and this is second peak overshoot. So second peak overshoot to the first peak overshoot ratio is the decay ratio. These two are the features based on which the controller tuning is to be selected. One is decay ratio. Decay ratio is the ratio of second peak overshoot to first peak overshoot, and other feature is error. There are several error values, and the error values are, this is integral square error, ISE is the integral square error, then integral absolute error, and this is integral time absolute error, integral time and absolute error. So these three are the major error parameters. Integral square error is defined as, this is the square of error and integral over the time period, that should be minimum. All the error signals should be minimum value. This is integral absolute error. Absolute error is the integral of et dt, and integral time and absolute error, that is integral absolute error multiplied by the time factor, should be minimum. So all these parameters should be satisfied for controller tuning, and the most measurable feature is decay ratio. That decay ratio, since there occurs number of oscillations before reaching the steady state, so the decay ratio should be within 1/4. In most industrial processes, this IAE, IAC and ITAE are not easily measurable, but the decay ratio can be easily measured. So 1/4 decay ratio is the major important criteria that is to be fulfilled in order to select the parameters of a controller. But for best performance of the process, all these 4 parameters should be satisfied. Now, different tuning methods has been proposed by different workers, that is by different set of researchers. Different methods has been proposed. The first method is ultimate method of Ziegler and Nichols. The researchers are Ziegler and Nichols, and this is the this is called ultimate method because the method of the controller, in this method of the controller is placed in closed loop and in proportional mode only. All these methods are purely experimental, so we should learn the methods, how they propose the models and what are the findings, and these formulas are directly applicable for designing the controller using this method for all standard tuning methods. So for typically this closed loop Ziegler-Nichols method or ultimate method, the controller is placed in closed loop and in proportional mode only. The gain of the controller is increased from the initial values, from the low value in step, and how long it will increase, that is when the controller value control variable variation time, it is found that at low gain the control variable overshoots and undershoots about the desired value with decreasing amplitude due to damping. That we all know that due to the damping, the for low gain value the control variable overshoots and undershoots about the desired value with decreasing amplitude due to damping effect of the process, and at very high gain the control variable oscillates about the desired value with constant amplitude. This is the method of oscillation of constant amplitude. So the response characteristics, this is the constant oscillation. That means the gain of the controller should be chosen in such a fashion that rather initially during experimentation the controller value or the gain value was chosen in such a value that the constant oscillation performed. So due to this constant oscillation, this is called the ultimate gain, or this gain value is called the ultimate gain. Suppose this let this gain of the controller, for which this continuous cycling of the process variable with undiminished amplitude, that is the constant amplitude, is determined at the value of Ku. That is the ultimate gain of the proportional controller. The controller initially set at proportional mode only, and the gain is increased in such a way that constant oscillation can be achieved. That is the that is treated as the ultimate gain Ku for constant oscillation, and the time period, this is the time period of oscillation, this is Tu, and the proportional band of the corresponding oscillation, for corresponding gain of the controller, the proportional band is Pbu. That is, ultimate gain is Ku, ultimate band is Pbu, and ultimate time period is Tu. And other modes, during experimentation the proportional mode was set initially, then applying mathematical models, the researchers found that for PI mode, the gain is 0.45 of Ku, PB value is 2.2 PBU, and the integral value Tu by 12. There is no experimental proof of these values, but these are the models, and these values should be considered for designing a controller using the Ziegler-Nichols method. So these should be considered as the formula for controller tuning. So this is the standard method of Ziegler-Nichols, and this is for constant oscillation. And as we all know that constant oscillation is not acceptable for a real system. So another model proposed by Harriot is damped oscillation method, where a damped oscillation is allowed. For the ultimate method may not be applicable for the process where sustained oscillation with the increasing amplitude may not be permitted. Actually, for most of the processes, these sustained oscillations are not permitted. To avoid this, another model is proposed by Harriot, that is damped oscillation method, and this is most common method, that where the damped oscillation, again this is initially experimented with proportional mode only in closed loop method, and adjusted from the oscillation of the and the decay ratio. Damped oscillation means how long the damping is allowed, that is that decay ratio should be 1/4. For the model, the decay ratio is 1/4, and under this condition, the time period, this is the time period. Decay ratio means the second of a shoot to first of a shoot, and the time period is TD. The value of the gain is taken as the optimal value of the proportional mode of a PID controller, and the integral and derivative action, this is again the from these experimental values, the mathematical, using a certain mathematical model, the parameter values are obtained as for PID controller. Kp is Kd. Kd is the proportional gain setting for 1/4 decay ratio. Tau I or Ti, that is the integral time action, is Td by 6, and tau d is Td by 1.5, where Td is the time period for the damped oscillation. These are the standard models, and we should accept these values as formula, because this is experimental method and to some extent mathematical modeling. And both the previous methods, that is ultimate method by Ziegler-Nichols and damped oscillation methods, both are experimented using closed loop method. This is another model for controller tuning for open loop method. This is the open loop method by Cohen and Cohn. This is basically an open loop technique. Open loop means manual mode of operation. See, this is the open loop system, where the manual mode of operation is considered, and at steady state condition with the process control variable maintained at the steady state value. Now, if the step change occurs, then what will happen? The response characteristics. So initially it starts from, this is the response characteristics, initially starts from 50% opening position, as we already learned from the controller operation, that initially controller starts from 50% operating positions instead of starting from 0 or full open position. So this should be 100%, not that one. One mistake is there. This should be extended up to this, sorry, up to this, and this value should be the 100%, not this one. There is a mistake of leveling. This should be 100% value. That is, starting from 50%, the response characteristics reaches to 100% position. That is the process reaction curve. And we are already familiar with the process reaction curve. And from the slope of this process reaction curve, the maximum rate of change of process variable is determined drawing the tangent. The time axis, at point A, it cuts the time axis, and the tangent is extended. That is, this is the time value LR, and this is the AC from which the tan theta can be determined. That is this is the theta value. So tan theta is AC by BC. So this is LR, the time value, and so AC, this value is LR into RR, where RR is the tangent. The slope of the tangent is measured from the curve, and this slope is equal to the process reaction rate, that is RR, that is equals to tan theta. So that can be determined from the response characteristics. This is the initial nominal operation point or initial steady state value starting from 50% opening position, and this is the 100% opening, that is the final steady state value after step change of final control element. For the step change of final control element, the response characteristics looks like this, and by drawing the tangent we can find the maximum rate of change of process variable, that is the process reaction rate, RR. So from here the values can be determined. Then for PID controller, the process gain is the final change in steady state in percentage by the step change in controller output. As we have calculated this process gain relationship with PB. So this is the final change in steady state value, means the steady state value minus the initial value. This is the final change in steady state. So final steady state value minus the initial value by step change in controller output. So final steady state value in percentage due to unit step change of final control element minus the initial steady state value in percentage. So finding the process reaction rate LR, the time value process reaction rate RR, time value LR, and the gain, process gain K, the index of self-regulation is defined by Cohen and Kuhn. This is purely from the model of Cohen and Kuhn. This is experimentally found, and then the mathematical model as proposed by the researchers. So the self-regulation index mu value is equals to LR into RR by K, and from that the different modes P, PI and PID modes are the gain values, and the other parameter values, that is TI and TD values, that is the integral action time and derivative action time parameters in terms of LR, RR and K are defined as LRRR and self-index value mu. Using these three values, the all the three parameters, that is for proportional mode Ki or Kc, for integral mode Ti, and for derivative mode Td, are to be determined using the Cohen and Coon model parameter values. And the we have already discussed in programmable controller section that integral wind up and bumpless transfer. So we should not discuss these values, these features once again. I think we need not to discuss these features again. So these are the controller tuning methods, and there are some other models of controller tuning available in book, but as many as model we will consider. Even today, several researchers are proposing different tuning methods, because there is a scope for improving the tuning performance of a controller, because the controller performance is purely dependent on the tuning parameters. So there is a ample scope of improving the tuning features. So lots of models are available. But all these models are experimental models, and based on their performance, a mathematical model is proposed for finding the parameter values for a PID tuning parameters. So that's all about the tuning chapter.